Hi, welcome to the sort of the makeup video lecture for the half of a lecture that we missed out during the week that we had an ACS conference a little while ago. And sorry for the gap here, and also sorry for the late release of this video, but hopefully you have a chance to take a look at it. We're picking up where we left off on this page here. I think during class we talked about the two products that we get here. What we said was that with the harsh reaction condition, like lithium aluminum hydride, remember that's a very strong reducing agent, one that I'm even kind of a little bit scared of. I did have a fire once. I think I'm still a little bit traumatized by that, but it wasn't that bad of a fire. And one lithium aluminum reagent that I'm pretty comfortable dealing with would be this one. It's not as scary or reactive, and for that reason you don't get the reduction from acid chloride all the way to the alcohol like with lithium aluminum hydride, but the reduction stops halfway at the aldehyde steps. So how does the mechanism work with acid chloride? The main difference here is there's no proton for this aluminum hydride to react with, to do acid-base reaction with. And so for that reason, the first step is not going to be a production of hydrogen gas, but the production, nucleophilic addition of hydride into the carbonyl carbon here. Okay, so the hydrogen here is not shown, but it's understood to be at that position. And once the chloride is able to leave, like shown, you would end up with the aldehyde product. Now, this is where the lithium aluminum hydride with 3-TB-toxy group attached to the aluminum would stop at. That's tri-TB-toxy aluminum hydride. But if you have lithium aluminum hydride, you still have 3 more hydrogens. After coordination of the oxygen to the aluminum, you would regain this negative charge, and so for that reason, that aluminum becomes once again a good and strong hydride deliverer. Maybe we can add that here. Deliverer. I hope I have this right number of R's and whatnot. But anyway, so it can deliver another hydride. I just want to point out there's a hydrogen at that position, but that's just not shown. And after the second hydride delivery, I just want to point out that the second hydrogen, it's just not shown, right? We would get to this point, and this is really the product. But after you do your acid aqueous workup, right? You can have water coordinate the aluminum and hydride reacting with hydrogen ion or proton of the acidic water and so forth. And hopefully you can imagine how the reaction turns out. Like initially there would be 2 hydrogens on the oxygen with a positive charge on oxygen. Those acidic protons come off and so forth to get to aluminum with 1, 2, 3 hydroxide attached to it. That is part of the mechanism. I'm just omitting those steps just because of the redundancy. But if I were to ask for a mechanism for this on a test or maybe ESA, I want you to be able to even do the redundant steps. So I would encourage you at home to work out these steps as well, maybe on a separate piece of paper. But the main important step in the workup is going to be how the aluminum gets a negative charge once it has 4 things attached to it. And oxygen here would have a positive charge once it both has the hydrogen and aluminum attached to it. That's an oxonium ion at that point. And the only way to resolve these 2 charges would be for that bond to cleave by moving the electrons over to the oxygen like so. So that'll produce the neutral product and aluminum trihydroxide. Now, how does the aluminum tributoxy hydride work? Well, it works the same way, like so, and it goes through the intermediate. It looks like that with a hydrogen, which doesn't necessarily need to be shown, but after the collapse of the tetrahedral intermediate and leaving of the chloride, it gets to the aldehyde, but because it's too bulky to coordinate, right, it can only deliver one equivalent of hydride, and plus just to ensure that there's only one hydride on the aluminum here anyway, so that's why the reaction stops at aldehyde, or I should say reduction stops aldehyde. So praise the Lord. So that's a nice way to make aldehyde from acid chloride. Okay, so that's all that we want to share about reduction, and now we want to get into discussion about the chemistry of esters. And what we want to do is to first talk about the Fischer esterification, which you're familiar with because you've done it, and we've talked about the mechanism at least in the context of the lab manual, and that's an important reaction because this is one way to synthetically produce an ester, and esters are an important class of molecules in nature, especially. When we did the Fischer esterification lab, we talked about how they are a great source of usually a pleasant smell. And interestingly, if you hydrolyze an ester and reveal a carboxylic acid, the carboxylic acids usually smell horrible. Like you guys might recall butanoic acid, is basically the pure essence of like human BO and whatnot. And that's because that's the byproduct that bacteria produce when they digest our fat and protein that comes from our sweat and whatnot, or just stuff on our skin surface, but mostly in sweat. Those bacteria can thrive, and especially under certain conditions. But some esters, on the contrary, unlike bad smelling carboxylic acids, usually smell good. Bigger esters that are not volatile, like wax, these are wax, like gigantic ester molecules, or fat molecules, or we call these triglycerides sometimes. Maybe we'll say triglycerides, or fat. It's called that because it has 3 ester functional groups. Those are examples of esters in nature. But what is the chemistry to make ester functional groups? So let's think about that. And even in nature, when enzymes make these esters, the catalysis is the same. Catalysis mechanism is the same, and you combine an alcohol and a carboxylic acid to make an ester. Maybe I'll make the new bond red. And the byproduct is water, and hopefully you see how 2 hydrogens on an oxygen is eliminated. So that would be this hydrogen and these HO together make up water as a byproduct. So for instance, if you mix acetic acid and ethanol in the presence of acid catalyst, this is a catalyst, you would get an ester, and this would be the product. And I want you to know that this right here is the new bond that we just formed, the ester bond. How does the mechanism go? It's the same old mechanism we've been talking about, isonucleophilic substitution mechanism. The only thing is that this carbonyl carbon is kind of a not very good electrophile because it's surrounded by so many lone pairs of electrons, so that nucleophiles who are rich in electrons would have a hard time attacking that unless it's sufficiently activated by being protonated by a strong acid like sulfuric acid. Okay. Like this. And that would lead to the tetrahedral intermediate, of course. And it would be right here. At this point, right, like, remember we talked about before, there's just too many electrons crowding this one single unstable tetrahedral intermediate carbon. Now that is sp3, so it needs to collapse, and when it collapses, it'll spit out something. If it spits out this alcohol, we would just go back one step. So remembering that these protons can move around via rapid proton transfer. Oops, that's not our we could have this intermediate collapse, and if it does, it can kick off on water. And we're here, and we could, once that extra proton can come off, we have our product, ester product, neutral ester product. Okay, so at this point, it might be good for you to pause the video and see if you can predict the product for this Fischer esterification reaction here. All right, I hope you had a chance to pause the video, and I want you to know that it's these three atoms that become water in leaves in the process. So the ester that you would form be that ester. Okay. That ester. All right. I wanted to cover this reaction at the same time because it is the exact same thing. The only thing we're kind of doing differently is instead of having a carboxylic acid starting material, we have an ester starting material. Why does this matter? Well, sometimes what ends up happening in a course of reaction is you expose an alcohol and a strong catalyst to an ester, and I just want you to be aware of what happens to an ester if that were to happen, because this would be really akin to the next reaction we'll talk about, which is hydrolysis. Okay, and in hydrolysis reaction, you end up revealing the carboxylic acid from the ester. Transesterification, you're just swapping out the ester, the alcohol portion of the ester. So right now, if this is the alcohol portion of the ester, or the portion of the ester that has its origin in alcohol, that can be swapped out with another alcohol like so. That's the main message here. And we're just going to show a very generic mechanism because you could swap out the R or R prime group with anything you want, and this still works the same way. Again, the same idea, nucleophilic addition step. Once the carbonyl is activated by an acid, you get to an unstable tetrahedral intermediate, which will have to collapse. And when it collapses, if the proton happens to be on the alcohol portion of the ester that was there to begin with, that's the part that can leave, right? And again, once we perhaps expose the carbonyl by removing the extra proton so that it's neutral, then we get our ester product. Okay. And at this point, it would be, again, a good point in the video for you to pause this and try these examples shown here. Okay. Hopefully you had a chance to try these problems and predict the product. If we were to transesterify this ester, ethyl ester, this would be ethyl benzoate. After transesterification with methanol, this would be methyl benzoate. So this portion comes from methanol. Okay. What about a cyclic ester like this? I want you to know that this is called a lactone. And to be more specific, the oxygen is on alpha, beta, gamma, delta. So this is called a delta lactone. What if it transesterifies? I want you to notice that the alcohol portion of this is this part. So that's going to be swapped out with the ethanol. And this would be a good reaction to think about the mechanism, okay? Because otherwise you might erase things that you shouldn't. So I would encourage you to pause the video here. 1, 2, 3, 4, 1, 2, 3, 4. And see if you can work out the mechanism there. The key intermediate being, again, the tetrahedral intermediate. That would look like that. Right, once the ethanol attacks the activated carbonyl. Okay, and from there, this oxygen would be protonated and leaves. That's the idea. And that's the same oxygen as this oxygen, okay? And then where we're gonna go from here is on Wednesday morning, we're gonna pick up from here the transesterification reaction. Same reaction, but with under a basic condition. And then finally, we'll talk about hydrolysis reaction of esters to go back to carboxylic acid and alcohol, and application of that for making soap molecules. Okay, so that's where we're heading with this. I'll see you